Okay, so I'm going to make a start. So today we're looking at the second half of exception handling, and we're going to look at some dynamic memory management and how we might continue to go about designing smart pointers. Right at the start, I'm just going to point out a couple of notices. First one is assignment 1 results are out. You can view your feedback by going to a university computer and typing CS6771 collect ASS1, and that will give you your feedback. If you scroll through your code, the tutors will have either put feedback throughout your code or at the bottom. Also at the bottom of there, it will say who it got marked by. So generally your tutors marked your assignments. For Dave's tutorials, I marked your assignments. If you have questions, email whoever is marked at the bottom as having marked your assignments. People did extremely well on assignment 1, which is good because it was meant to be easy. But you guys did better than I expected, which is really good. Every single person who submitted assignment 1, their code compiled. It's the first time I've ever had a class where every single submission actually compiled. It was pretty impressive. The average mark was 8.5. Average mark was 8.5, so that's extremely high and extremely good. Just means we have to make the rest of the course harder. There's a lot of issues with assignment 2 at the moment, though. I was expecting some issues. We're smacking into a couple more issues than what we were expecting when we first released it. So I'm regularly updating the course notice board with pointers or tips or problems that people are facing. Most recent update was yesterday. We've decided that we're not going to require you to have a constructor that works for standard array. It's causing people too much issues. So you do not need a constructor that takes an iterator to a standard array. You still do need a constructor that takes an iterator for a vector and for a list. You can either do that through creating a couple of constructors, or you can do it through a templated constructor if you know how to do templates. The template required for the constructor in assignment 2, if you do go down the template path, is very, very, very simple. We haven't talked too much about templates yet, but for 2 slides from last week, where we briefly mentioned templates, that is more than enough detail for you to be able to do the templated templated constructor for assignment 2. But if you don't want to do that, you can do it like a normal constructor and it'll be fine. People also having other bits and pieces of problems. In particular, if you get a compile message that says something like cout is not a member of standard, it's simply because you've forgotten to hash include iostream. Your hash includes need to go in your .h file. Lots of people put their hash includes in their .cpp. Your library hash includes should be in your .h file. Also, be very clear when you go take a look at the testing instructions. There is a sample make file down the bottom of the assignment brief that says we create Euclidean vector.o for this compile command. We create Euclidean vector.o for that compile command. We create the Euclidean vector tester executable through that command. Separate out your compilation steps, because that is exactly how we'll be doing them when we compile for testing for assignment 2. A lot of people are not separately compiling their Euclidean vector.o. If you don't separately compile your Euclidean vector.o, it might hide some problems with your code, some compilation problems with your code. So make sure you follow these instructions and do it this way. Other things to do with assignment 2, just to note, template functions, if you do use them, templated functions for definitions need to be in the header file. The template functions work slightly different to normal functions. We're going to talk about templates next week, okay? But if you do go down the templated route, they need to be in your .h file. If you do go down the template route, you might have some problems as well with one of the other test cases I posted last week. And so there's a partial solution to how you might deal with some of those. Again, people are having more problems than I was expecting. That's okay, we can have problems. Keep posting messages to the course message board. It's probably one of the best places to post things to. It is public to everyone, okay? If you have a personal problem, email me, don't post it there. But if you have a general question that other people might be also having problems with, post it to a message board. It's the best place to put it because that way I can respond and other people can see what problems you had. Okay, let's kick into what we're looking at today. On Monday we left off looking at exception handling, and we looked at try and catch blocks, and we looked at the idea of having exception objects. Today we're going to continue looking at how to catch exceptions, and particularly exception guarantees and dynamic memory associated with catching exceptions. And what we're working towards is smart memory management. We're not going to get all the way to completely through smart pointers today, but that's what we're working towards. So here is a small program that demonstrates what we call stack unwinding. We have a main function that comes in and calls a function f. Function f then calls a function g, and then we go into function g. And on the call stack, okay, so we've got a memory stack, we also have a call stack. A call stack is the order in which functions get called. On the call stack, at the bottom of that stack, we have main. The next step up, we have f, and the next step above that, we have g. Out of g, we throw an exception. The exception is not caught inside g, and so what happens is it gets to the end of this brace in line 5, and g gets removed from the call stack. Falls literally back to f. We were inside f before we call g on line 8, but we're throwing an exception. So line 9 doesn't get executed. We tumble our way through f looking for a catch. There is no catch inside f. So f comes off our call stack, and this line 9 actually never gets executed. We fall back into main, and there is the catch. And that catch block gets executed. After the exception has been caught, line 18 continues. This is the same process as if you've done exceptions in Java. But what you should be seeing at this point is G through the exception, F didn't catch it, and so G and F both got unwinded. It's called unwinding, it's called stack unwinding, and it got unwinded from the stack until we got it caught. If main had not caught the exception, the program would have terminated. And so your runtime stack looks like that. You've got main and then F on top and then G on top of that. And so stack unwinding is the process of exiting from call frames in the search for an exception handler. Now if a new exception, so if a second exception is thrown during the stack unwinding process, and it's not caught in the same function that threw it, terminate is called. Terminate exits your program. So if you throw an exception, the first exception that you throw, if you throw an exception, tumbles down the stack until it gets caught. If in the process of tumbling down the stack, a new exception somehow gets thrown, then unless it is caught within the thing that threw it, then terminate is called. Okay? So, how does this work? Let's look at destructors. Now, remember, a destructor gets called when something goes out of scope. As we tumble down the call stack, things go out of scope. So their destructors get called. Terminate gets called as well during stack unwinding if an exception leaves a destructor. Okay? So maybe our call stack's not just main, F, and G. Maybe our call stack contains some member functions. If that member function throws an exception and it's not caught before the object that contains that member function gets destroyed because it falls down this call stack, terminate gets called. You cannot have an exception leave a destructor. The reason for this is resources may not be released properly if an exception leaves a destructor. They may not be cleaned up correctly. Now you can catch an exception in a destructor. You can throw an exception inside a destructor, but it must be caught inside that destructor as well. If it doesn't, your program terminates. Now all STL types guarantee that their destructors are non-throwing. Okay? So if you end up with a problem with terminate being called because an exception is left a destructor, it's your problem, not the STL's problem. The STL guarantees this isn't going to happen this way. So let's take a look at exception handling and object destruction. In C++, all fully constructed, non-heap objects are destroyed automatically. What's a non-heap object? It's a stack object, or it's a static object. So we looked at the static objects and stack objects and local objects. On Monday, we also looked at heap objects. And we talked about the difference between named and unnamed objects. Okay, so anything that's not on the heap is destroyed automatically by the compiler. Okay? And they're destroyed at the end of their defining blocks, so for bracing, and their destructors are called for releasing resources. So here's a very simple example. Int main says try f. You go into f, it creates a local variable on the stack, local string on the stack, it's called s. It then says throw 100. The next line never gets executed, okay, because it's thrown now. The end of this function, unfortunately, it's been placed there by the slides, okay, but you'd expect that to be on its own line, okay. At the end of this function, the destructor for the string is called because it goes out of scope. The exception gets caught down here. Okay? So this line here didn't get executed. This object here got destroyed because it went out of scope after the throw. Okay, because the stack got unwound. And this is fine because this is a stack object. It's a local stack object, no issue. On this next slide, here's the same thing again, using dynamic memory. String pointer s equals new string, C++, through 100. This line doesn't get executed. What happens with this dynamic memory up here? Yep, pointer gets destroyed, but the string is now just a memory leak. Okay, because this is heap memory. Okay, pointer got destroyed, so star s got destroyed. This new string did not get destroyed. Okay, we've got a memory leak. How do we handle this? Anyone got any ideas? Maybe one solution is don't use dynamic memory. Probably a dumb solution, but maybe one solution to this problem is don't use dynamic memory. Okay, but we want to use dynamic memory. So what do people think the solution to this problem might be? Maybe think back to the end of Monday, whereabouts we looked at, I'm going to end up giving the solution away. What did we look at the end of Monday to do with catching exceptions? And somebody somewhere had a question about how does it work. What did we look at? How might we handle this problem? You just yell it out. Sorry? Oh, you can throw the string itself. Yeah, okay, that's one way of doing it. Yep. So that wasn't quite where I was going, but yes, you could throw the string itself. But imagine if we had a series of dynamically created objects at that point. No, the reference isn't going to solve this problem.
Can you catch it inside the function, clean up the memory, and then rethrow it?
Yeah, that's the solution. So, I think I've got one of these. Oh, no, I don't. I had a slide. I seem to have lost the slide. Yes, you could catch it inside the function f, clean up the memory, and then continue to throw the exception again. Remember we had that throw inside the catch? Yep, could do that. But that starts to get quite messy in terms of what your code looks like. So it's not a good solution. Okay? But it's a better solution than what we've got here, because at the moment we've got a problem. Okay? So, this is the first time you're going to see a smart pointer, as in a C++ 11 smart pointer. We're going to go into a lot of details on Monday about how these things work, or at least what's available. But we can create this thing called a unique pointer. And to save space on the slide, I've said auto here, but you could also say standard unique pointer, standard string, in place of that auto. And so this auto pointer, or the smart pointer, wraps the string in the smart pointer object. It's very similar in terms of its design to how this string pointer class that we looked at last week looked like. Okay? It's a wrapper around a dynamic piece of memory. And so now, when we go out of scope because of this throw, this unique pointer object gets destroyed. The destructor for this unique pointer object knows it needs to destruct or destroy the thing contained inside it. In a very similar way to how our string pointer on line 6 on the right hand side destroyed the pointer to what it was storing last week. Okay, but this is the nice C++11 way of doing it. You don't have to manually go and write your own classes to handle this. Okay? If you're getting technical, this covers the idea that resource acquisition is initialization. So you should encapsulate resources, e.g. memory, locks, etc., inside objects. So you wrap your dynamic memory, you wrap your object, you wrap your resources that you're using inside some objects. And you acquire resources using constructors. You then use destructors to prevent resource leaks. Okay, it's a nice, clean way of dealing with it. You've still got all the exception throwing and stuff like that. You've still got all that functionality, but this is going to prevent a memory leak because you've got the object handling the memory for you. But what about constructors? What happens if we have a problem inside a constructor? So I've got a class here for book, and this book maybe has a cover, so an image associated with it. Maybe it's an audio book. Maybe it's also got an audio clip associated with it. Okay? And these things are pointers. Inside the constructor, for a book entry, I copy the name, because the name was a string, and I copy the name of the string there. Okay, and the string is here, that's a stack object. But then, for the image and the audio clip, okay, I go and create a new image and a new audio clip object. Now imagine an exception occurs during the construction of the audio clip. So the third thing that we do, okay? That, when it unwinds, will cause this book entry object to be destroyed, therefore destroying this stack object string, but the image object up here will leak because it's not fully constructed. Okay, so the destructor doesn't get called the same. Okay. The problem, we've got a memory leak inside a constructor. How do you think we solve it? You got any ideas how we solve this? Now, one silly solution, but it's actually in the Google style guide for C++, okay? That's one of the times I really disagree with it. One really silly solution to this is have a constructor that basically does nothing, and then have an initialization function that goes and actually initializes things. It's really silly because it defeats the purpose of having a constructor. And again, there's some things that you can only initialize in constructors. Things like const objects. You can't initialize a const object outside of a constructor. So the solution to this problem is not have an empty constructor and then have an initialization function, despite what the Google style guide tells you. Okay? What else might be a solution to this problem? It's very similar to the solution to what someone suggested before, and I told them was a solution, but it's not the smart solution. So you can say it again. What do you think might be?
Catching the current object in the constructor.
Yep, like that. So I can have a try and a catch inside my constructor. It catches and destroys stuff. Quite messy code again. Okay, so this is less than ideal. And again, if we go and use C++11 smart pointers, we wrap these things inside these pointer objects. Okay, so this unique pointer object is on the stack, even though what it stores is on the heap. So we have an exception get thrown somehow, and because these are stack objects, their destructors will get called, their destructors will know how to manage the resources contained within them. Okay? And so that's one way we can, that's actually probably the correct way in which we can solve this problem. Okay, we're following this so far? So we still have exceptions, they can still be thrown, they can still be caught. What we're trying to prevent is memory leaks. Okay? But throwing exceptions, even though it's good for handling problems, if it's not handled correctly, there's lots of ways you can get memory leaks. And we're going to come back to that in a few slides. In the meantime, let's talk about exception safety and exception specifications. I showed you this last week a little bit, particularly for some of the move constructors and for destructors. You can tag a function to say no except. Tagging a function as part of its declaration as no except says that this function will not throw an exception outside of it. Not having the tag there says it might throw an exception. By default, all constructors or move assignment operators or destructors are tagged as no exception throwing. Okay? But a violation of this exception or specification is only detected at runtime. So you can perfectly validly write code that said void if, no except, throw exception, and this will compile. At runtime, it goes, wait, hold on a second, you said I wouldn't throw an exception, and I'm having an exception thrown through me, and your program terminates. Okay? A no except function can catch exceptions within itself. It can have a try and a catch inside itself, and that's perfectly fine. So a no except function can call other functions that may or may not be tagged no except. It just needs to guarantee that if one of those functions that's called throws an exception, that gets caught before it goes out of that exception, or out of that function. Tagging functions no except enables some compiler optimization. So, standard vector will call its move constructor to move elements for some operations if there is a non-throwing, so if these operations are non-throwing and it can use those things, so it's calling a move constructor for some operations. If there's a move constructor available, it's non-throwing. Otherwise, it'll call a copy constructor. So using non-throwing exceptions enables some compiler optimizations. You can also pass an argument into no except. And so I can declare a function f and say to it, this behavior of f is the same behavior as g. So if g is non-throwing, then f is going to be non-throwing. If g is throwing, so you can say no except true, false. Okay, so no except true says this isn't going to throw an exception. No except false says this can throw an exception. You can make this behavior determined based on somebody else's behavior. Okay. Now I don't actually expect you to necessarily now go through all your code and change everything to no except. Okay. What I do expect is you to have an idea of what no except is in terms of tagging, saying something won't throw an exception, and have the idea that if something does throw an exception, that terminate will be called.
What's the point of having the exception based from another functions, whether that throws an exception, so it's going to be static at file time?
Again, if you know something about the library you might be using, or maybe you're swapping out some different libraries. Okay, so standard library, because everything's no except, is probably a bad example, but imagine that you were swapping out between a vector or a list, and maybe the vector was exception throwing and this wasn't exception throwing, that service you can make it dependent on that. Again, that's not a valid example because the STL guarantees things won't be throwing, but it allows you to do that sort of behavior. Okay? So there's 4 common levels of exception safety, and this is a bit of a wall of text, this slide. Okay? But there's no throw guarantee, okay, which is known as failure transparency. Okay? So this is when operations are guaranteed to succeed and satisfy all requirements, even in the presence of exceptional situations. If an exception occurs, it will be handled internally and not observed by clients. Okay, so this is basically a function is tagged no except. And this no throw guarantee is if anything goes wrong inside this function, it will sort itself out. It's guaranteed to sort itself out. Okay? There's a strong acceptance safety. It's also known as commit or rollback semantics. So operations can fail, but failed operations are guaranteed to have no side effects, so all of the data retain their original values. Say if I was replacing some data. Okay, I had some function that was called replace, and replaced some data. A strong acceptance safety might guarantee that that replace is either going to completely happen or not happen at all. You're not going to end up in a situation where some data gets replaced and the rest of it doesn't because some sort of exception got thrown. Okay, so strong exception safety says something might happen, but if it happens, I can recover from it, I can roll back, and there's got to be no side effects. Basic exception safety is also known as a no-leak guarantee. Partial execution of failed operations can cause side effects. Maybe half your data was written over, okay? But all the invariants are preserved, and no resources are leaked, so you don't have memory leaks, okay? Any stored data contains valid values, even if the data has different values from before the exception. So our replace had a basic exception guarantee with basic exception safety. Half the data got modified, but it's still valid data. Probably not for data you want, but it's still valid data. It's not corrupt. And then this the idea of no exception safety. And no guarantees are made about the data before or after this function is called. As you can probably imagine, to correctly do a no-throw guarantee and with strong acceptance safety, it's going to take a lot of time. And so we look at this idea of things that could be potentially throwing, and these things that are irreversible mutations. Allocating memory doesn't take much time, but there's actually no guarantee that you actually get from memory. Okay, so if it's out of memory, something gets thrown. Copying some data could potentially throw. There's no complete guaranteed behavior on that. Destructing some objects takes time because you want to ensure that object is correctly destructed. Deallocating memory takes a lot of time because you've got to destruct all the objects and then correctly deallocate the memory. Okay? And then operations that may throw but don't do anything, they're irreversible. Operations that may be irreversible but don't throw. Okay, so there's these exception guarantees, and the more complex they are, the longer the time takes. Okay, because you're handling all the edge cases. Handling edge cases takes time. And here's an example, okay, you don't need to understand all this code, but what you do need to understand is maybe I've got this reverse function here, and it's reversing a stack or an array or something, okay? Forget about understanding the code on this slide. What you do need to care about is there's some sort of copy to new storage, and it can throw some exceptions. But if something goes wrong, it releases the contents of them. Only once this memory has been correctly allocated does the irreversible mutations begin. The old memory is deallocated and changed around. So see the structure of the code. Okay, forget about what the code does, it's the structure of the code that matters. The stuff that would cause problems is up the top and is safely handled. Only once everything is good does the destruction of old memory begin. But again, this is complex. It requires you to think about all the problems that can go wrong. And so we still want some smart ways of being able to do memory management. So say we have a sparse matrix. Okay, this is actually the assignment last year. Instead of a Euclidean vector, they had a sparse matrix. Imagine you had a plus operator to add two matrices or two Euclidean vectors together. To do this, you might create a new sparse matrix object and copy in the left-hand side, and return that new object plus equals the right-hand side. Okay, this was the slide for how to do plus operators from about 2 weeks ago. And this is efficient in C++11 due to move constructors and move assignments. But you're doing a copy there, or in C++11 you're doing a move assignment. Okay, so there's quite a bit that's going on. You could make this code efficient by creating a copy there, doing C plus equals B and returning a reference here. But this is incorrect, as you should be able to correctly identify, because you're returning a reference to a local object. And that local object is going to be destroyed when it goes out of scope. So that's efficient but wrong. Another way you might do it, create a pointer, create this on a heap. Okay, that's missing the copy constructor call, but that should be a copy constructor copying A. And then you can return plus equals B there. But then the question is, who then becomes responsible for destroying that object later on? Who has ownership over that piece of memory? That's what we might talk about. And so when objects are large, we generally use heap objects. But pointers are a burden on users. They require memory management techniques, smart pointers, reference counting, handles, okay? To enable people to not have to manage pointers explicitly themselves, because pointers are the biggest source of bugs that you can get. Pointers are evil. Powerful, but evil. And so you've probably seen slides like this already. Here's a memory leak. Okay, we create X. If we forget to delete X, we've got a memory leak problem. If an exception is thrown and we've got this ... is, delete X will probably not be executed. Then suffer from a memory leak problem. Two other problems that occur with dynamic memory is dangling pointers. We talked about those on Monday. So that's where you delete X correctly, but then you don't change where X is pointing to. So now it's pointing to a piece of freed memory. And if you then try to reference that piece of freed memory, that dangling pointer, you don't know what's going to happen. It may or may not work. It shouldn't work, but it may or may not work. You've also got the double free problem. The double free problem is whereabouts you delete the same piece of memory twice. And your code does not like you to delete the same piece of memory twice. And so again, the solution we looked at on Monday was delete something, set the pointer to it to null, and that way if you delete that thing again, you're only deleting the null pointer, and it's perfectly safe to delete the null pointer. Again, this is the slide that should have come earlier. A bad programming style for ensuring that you don't have this problem is this code here. Create X, try, catch, delete X, rethrow, delete X. This code is valid. Does this suffer from the double free problem? Who thinks it's got a double free problem? Anyone? Who thinks it doesn't have a double free problem? Okay, it doesn't because of the rethrow. So those lines down there won't be executed because that gets thrown out of there. So it doesn't have a double free problem. But see how people got confused, even just then. This is confusing code. And there could be cases where this does lead to the double free problem. Okay, so this is not a good approach. Again, talking about smart pointers, repeat of slides from last week. A smart pointer is simply an object that behaves like a pointer. So it overloads the arrow and it overloads the dereference to provide pointer-like behavior. Okay? And there's the code from last week, and it's up on the right-hand side. Okay? And so we can go into a little bit more detail about how this works. Okay? We have a pointer inside the named object, okay, and it manages for you. And so you can say string pointer p is equal to new string inside there, it gets passed into the constructor. When you go out of scope, it gets destroyed because of the destructor. Okay, revision from last week. But what about this problem? This nice smart pointer has a couple of big problems with it. I have a string pointer. I go into another piece of code, another scope, and I have a string pointer q, it copy constructs p. When q goes out of scope, what happens? So I've got my smart pointer p, and I have my smart pointer q, but q is copy constructed from p. Now, admittedly, actually, in my source code up on the right-hand side, I don't have a copy constructor, but that's okay. The default compiler version of a copy constructor is just going to copy that pointer. So the smart pointer in this case, with q and p, are both referencing the same piece of memory. That is generally how a pointer works. So we have two pointers assigned to each other, they reference the same piece of memory. That's fine, it's the correct behavior. But what happens when this smart pointer goes out of scope for the first time?
Freeze memory.
Freeze memory. Is that what we wanted to have happen? Probably not. So on the next line, if we try to print out size, like call p colon size to get the size of the string there, oh well, we've got a problem now. So that's not going to work, and then when we go out of scope here, well, we've got the double free problem. So our smart pointer didn't work. It wasn't that smart. It was a smart dumb pointer. Or it's a dumb smart pointer. So let's talk about reference counting. People know what reference counting is? One person? Okay. So reference counting is a way of doing garbage collection. Okay? And you can do it yourself to prevent memory leaks and dangling pointers and double frees and things like that. Okay? There's a couple of references that go into a lot more detail about how this works. Okay? But I figured I'd rather use the next 10 minutes to tell you about the details of how this works and going into for C++11 smart pointers. So on Monday we're going to look at the C++11 smart pointers, but for the next 10 minutes today we're going to go into quite a bit of low-level detail about how these things are implemented. Okay? So there won't be questions on reference counting in the exam. You will not be expected to do this, but this is the conceptual stuff of how reference counting works and how garbage collection works. I have a class here called point. This class point is a 2D point. It's got values I and j. Okay? This could also still be a string class, but we've changed it. It's a point class. This point class has private constructors. You cannot create an instance of this point class unless you have friendship or you're part of this smart pointer class. Okay? So we have this class called point. It has private constructors, so it can't be constructed by itself. It also contains an unsigned int that is a count. This is going to be our reference count. The count is going to be used to keep track of how many pointers or pointer objects are referencing this single class object, a single point object. Okay? So we need to create some factory methods to construct the point objects. We with us? Everyone with us so far? Yep. Okay, so I have a two-dimensional point. It's containing extra information about how many people are referencing it, and it's got private constructors. Here is our smart pointer for that class. I'm going to leave on the right-hand side the class there, and on the left-hand side I'll leave the smart pointer class, just so we can see it all. It's got a very similar syntax to string pointer smart pointer class. It has the operator in direction the arrow in direction operator overloaded to return the pointer. And see, this is a pointer down here, private pointer. Okay. It has the dereference operator overloaded. It has a constructor for a point object, okay, that pre-increments the reference count. So when a pointer object gets created, it references or increases the count to that point object, okay? So that underscore count is the underscore count contained within point. Remember, this is a friend class, so it can access its private member data. The destructor doesn't just delete the memory. The destructor pre-decrements the count, and only if the reference count is 0 does it delete that piece of memory. Okay, so its reference count is keeping track of how many things have some sort of reference to this thing. As more things gain a reference to it, the count increases. As fewer things have access to a reference, it decreases it. This is a similar but different concept to what we did in tutorials last week, whereabouts we had a static object counter. And do you remember we increased that object counter when we created things, and we decreased that object counter when we destructed things? Similar, related concept, it's not the same concept though. But our destructor does not explicitly delete the memory, it only does it when the count gets to 0. Okay? Copy construction. On the copy construction, we increase the count, because the two things are referencing the same piece of memory. Okay, so the copy construction, because it's a smart pointer, doesn't duplicate the data this pointer is pointing to, it's going to duplicate the references to how many objects are referencing that piece of data. Copy assignment. This one's a little bit tricky. Copy assignment. You're increasing the reference count to what you're assigning to. You're decreasing the reference count to a pointer that you were previously referencing, because copy assignment. Remember, you're replacing with your internal content. So you are already pointing to a piece of memory. You're having that location updated. So the place that you were pointing to, you're going to decrease its reference count, and you're going to increase the reference count to a thing that you're now copying over the top of. Make sense? You then copy that reference across, okay, like that. And we have some inline factory methods for creating a point, okay? Static factory methods for creating a point, okay? So these things all work. Let's take a look. Okay, so are we clear about how this thing works? You don't have to understand exact semantics of this. You will not be asked to write this, but do we understand how reference counting works? Yep. Let's take a look at a main method. The main method says, create me one of these pointer objects using the static create factory. Okay, I now have one object, and that object has a reference count of 1. I have a second point PTR object, and I say equals to 1. What do people think happens at this point? Let's break this down. How many pointer objects do I have at this point? No, how many pointer objects do I have? 2, right? That should be obvious. Yeah, everyone happy with that? Not 1, I've got 2. I've got 2 point objects. How many point objects do I have at this point? I have 1. Okay? I have 2 pointer objects. I have 1 point object, because those 2 pointer objects are pointing to or referencing the same point object, the same piece of memory there. So what is the reference count on that point object? 2. Good. Okay. That one's the easy bit. Let's go to the next line. Next line. P1 equals point create 22. Okay? Now let's break this down onto the right hand side first. This goes and creates a new point object and returns, the create function returns a reference to a point pointer object. Okay, if you missed that from a previous slide, I've moved up to the right hand side. So the create creates a new point object, and that's going to call a constructor there. Okay, so it's going to implicitly call the point pointer constructor. Okay, I could have done this in my code. Okay, this isn't actually my code, it's code already exists, but I could just, to clarify, do this. Okay, same piece of code, implicit constructor. Okay, so coming back to the left-hand side, point create. I now have 2 point objects. One point object has a reference count of 2. The other point object has a reference count of 0 initially. But remember, the create is going to return a point pointer. Okay, so it's going to create that point pointer on return. So now I'm going to end up with a point pointer object. And so that second point object is going to be reference counted to 1. Okay, so at the end of this create, when it returns, okay, now what do I have? I've got 2 named point pointer objects. I have 1 temporary point pointer object. Okay, so overall I've got 3 point pointer objects. I have 2 pointer, so 2 point objects. One is reference counted to 2, one is reference counted to 1. Okay, we're following this so far? Okay, it's getting a little bit tricky. Now, because this is copy assignment, P1. P1, point pointer P1 is currently pointing to our first point object that we constructed. I really should draw this as a diagram, but I don't have a whiteboard. Okay? That's going to decrement the reference count to that first object. Because it's copy assignment and move semantics and stuff like that, it's not, actually no it is. It's going to decrement, think about what's going to happen, it's going to decrement the first point object's reference count. So the first point object now goes back to having a reference count of 1. It's not going to destroy it because that point, original point object still has a reference count of 1. It's going to increment the second point object that we created inside this point create here on the second line, and its increment's actually going to go to 2. Now the constructor's going to optimize some of this out, but its increment is going to go to 2. Then because this is a temporary object, that temporary object gets destroyed and therefore it goes back to 1. Okay? We now end up with 2 point objects, both reference counted to 1. We end up with 2 point pointer objects pointing to 2 different things. Okay, we've followed this so far. It's complex, and again, the constructor, so the compiler optimizes some of this out. P2 here equals P1. Okay, P2 equals P1. What's going to happen? Move copy assignment P1 onto P2. What's going to happen?
The point that P2 was pointing to is going to decrease its references.
Yep, so the pointer that, so point object that P1 was pointing to decreases references to 0, so what happens?
So it will get destroyed onto the scope, and then the other one will have 2 references.
Yep, so that's going to get destroyed, and P2, okay, is going to increase. Actually, you're right, it's going to get reference counted dropped to 0. It's not actually going to get destroyed at that point. It's going to get destroyed when it goes out of scope. Okay? But then P2 is now going to have 2 references to next thing, to that second one. Okay? I have about 20 seconds before the lecture recording stops. So the next 2 slides, look at these in your own time. They look at new and delete. Okay, look at these in your own